So this is our first lecture on modern physics in the field of relativity. And on this first one, we're just going to talk about the Galilean transformations. So relativity is really how observers moving relative to each other compare physical phenomena that they measure. Right here. Now, relativity is a very old idea. Galileo first brought it up when he got in trouble with the church. When he got in trouble with the church saying the earth goes around the sun, they put him in house arrest. He couldn't bring it up anymore. But Galileo was a smart guy. What he did was he went out and attacked some of the arguments against it. One of them was, if we're going around the sun at tens of thousands of miles per hour, why don't we feel it? And that's where relativity comes in. So relativity really deals with observers and moving with respect to each other. So we need an observer. Usually you put an observer has some sort of a coordinate system associated with it. So we need to make up some sort of a coordinate system, say an XY coordinate system. Here we've got X in a Y coordinate system. So all observers have some referenced coordinate system. So what I'm going to do is I'm going to put people on this coordinate system, and this coordinate system is fixed relative to this board, relative to the floor. It's not moving right here. Since this is fixed relative to the floor, the person I'm going to put at the origin right here is Frank. Right there. He's never going to move from his origin. He's always going to be at x equals 0 and y equals 0. Out here, it's some other location right here. We have someone else using this same coordinate system. This will be, say, Fred. He's also never going to move relative to his coordinate system. So if he's at, say, x equals 5, y equals 0, z equals 0, he's always at that location relative to this coordinate system. We could have a person over here, it could be up in the tree, or it could be down here. And this one right here might be, say, Francis. Everyone, so there's a whole bunch of people all over this coordinate system. Their names all begin with F right here, and none of them are moving. But they all share this same coordinate system. So any observation, they're all going to agree on an observation right here because they're all using the same coordinate system. Well, now we need a moving coordinate system. So we need a completely different one. And to make life a little easier, I don't want it moving off in some strange direction. We're going to have it move right along the x-axis. So I'm going to put this one in red. So we've got some coordinate system that's going along here. So this is, in my red coordinate system, I'll call it x prime, y prime, right here. And this coordinate system is moving to the right at a nice constant velocity relative to Frank. So Frank's was at rest relative to the board and relative to the floor. This one is moving to the right at a nice v, which is a constant. Okay, and on the origin of this coordinate system is Mary. She's always going to be at x prime equals 0, y prime equals 0. And we could have another person out here. We could have Mark. Say out here, this is Mark. He's always at x prime equals, say, 5, y equals 0. He's never going to move relative to his coordinate system. We could have had Mo and Margaret and all the other people in red also. But that's the x prime. This is the y prime, x and y right here. Now, we're also going to say, this red coordinate system is moving off to the right here. At some earlier time, their origins were overlapping right here. And we're going to say, that's when we're going to synchronize their two clocks. So we're going to say, when t equals 0 and t prime, everything he measures is t prime, when t equals 0, when t equals 0 and t prime equals 0, their origins overlap. Origins. Overlap. Okay, and so we're going to use this nomenclature for the next 25 videos right here. This is what we're going to be using for all of relativity, this same nomenclature where Mary's moving to the right at a constant velocity v relative to Frank. You got to remember, Mary is going to say, no, I'm at rest, and Frank, you're moving to the left. But we'll continue right here. Okay. So, now, suppose some object is thrown through the air. It could be a projectile. Some object is thrown through the air, and let's say it's right there at some point. Well, at this point, Frank is going to see this object moving with some velocity. I can't use v because we've already used v for this right here. So here is, we'll use a different letter. We'll use u for whenever you measure the velocity. Okay, so Frank will say, oh, that has some velocity u. It has some x component of that, ux. Has some y component, uy. It has some angle theta in here. Okay. Now Mary, she might not agree with these right here. And so she's going to measure different speed and different components. So Mary's gonna, I'm just gonna draw it over here so we don't put it right on top of it. She's gonna measure some ux prime, and she gets a completely different u prime and a uy prime and a different angle, say theta prime. Everything Mary measures will be prime. Everything that Frank or all the F people will measure the unprimed. Okay. Now we could have done the same thing with acceleration. This thing has some sort of an acceleration. It has an ax and an ay. When Mary or Mark or whatever measure the acceleration, they'll say ax prime, ay prime, and a prime. And so relativity is really how do they compare their two measurements right here. Okay. So if we go to something like Newton's Principia, Newton. He said, in his Principia, he said certain phenomena certain parameters are absolute. He called them absolute. That means everyone measures the same, and it doesn't even have to be for this case right here. It could be whether they're moving this way or that way, or they're accelerating. It doesn't even have to be constant. Absolute means they always agree on it. And one of them is time. Time. That is, if Frank throws a ball up in the air and he measures how long it's in the air, and Mary measures it from her coordinate system, they will agree right here. And so what that means is whenever you measure time, it's really between a start and a stop. So really I could say t minus t naught, that's how the time, maybe t is when it hit and t naught is when they threw it. That's in Frank's frame, and that should be the same in Mary's frame right here, which would be t prime minus t naught prime. Well, we might as well start the clock when their origins coincided, and that would mean that these are both 0 all the time right here. And so we could have just said, so this is more or less saying that t equals t prime. Now he said something else is absolute, and that is space. When I mean space, that means the distance between 2 points. If Frank has a meter stick, measures it to be 1 meter, Mary going by will also measure it to be 1 meter, independent of whether she's accelerating or moving off in any direction right here. Now in this case right here, we're just moving to in the x direction, but let's just say Frank measures how tall he is. He says, okay, it's this height, the y minus y naught. Remember, a length is always a difference between two. Y minus y naught. And Mary, when she measures Frank height, she'd say it's y prime minus y naught prime. But they both will always agree on this y height, and because of the way we're moving. These are both 0 right here, y naught and y naught prime. These are both 0. And so you can say y and y prime, they'll always agree on. Okay, and if Frank laid down, so we had the z direction, we could do the same thing, and you could say z minus z naught equals z prime minus z naught prime. And so you could say the same thing with z. Z equals z prime. Now x, if you were doing it for x, we could say x minus x sub naught is equal to x prime minus x sub naught prime. But I cannot say that x is equal to x prime from that right here. Why? But I can say this right here. Why? Because this is moving out. I can't say x equals x prime because you notice they don't even agree here. So they only agreed when they were at the beginning spot. So we'll leave this one out. We at least have this so far right here. Now, Newton also said for this special frame, these are called, when you're moving at a nice constant velocity, we call these inertial coordinate systems, ones that are not accelerating. Inertial coordinate systems. Okay, anything that is, they're going to agree with these inertial coordinate systems, we call them invariants. Invariants. Okay, and Newton said that for this case right here, there is something that is invariant, and that is the force. The force on an object. If Frank weighs a certain amount, Mary measures Frank's weight, they're going to agree in this sort of a system. If this started accelerating, that wouldn't be true. So this is a little bit tighter than these. It's not an absolute. But for this case, we can say F is equal to F prime. Oh, also up here, we could have said M. Mass was an absolute. So I could have put mass up here. That was above this right here. M equals M prime. That is, if Frank measures a this an object to be 2 kilograms, Mary will always measure to be 2 kilograms. So here's a lot of things that they compare. They're equal. But suppose we wanted to say, how does the x and the x primes compare? Well, for that, it might be easiest for us to draw this a little bit differently. Instead of making it an xy coordinate system, y doesn't do much right here. So instead of an xy coordinate system, what we'll do is we'll make this a xt coordinate system. This is Frank. This is for Frank. This is x and t for Frank. Well, what's going to happen if we just looked at Frank right here? Well, at t equals 0, I know where Frank is. He's at his origin. Well, x equals 0, he's right here. Well, but Frank is always at his origin. He's always at x equals 0 for any time. So what that's going to do is, this point is just going to start moving up like this. So there is what's happening to Frank on this coordinate system. He's just heading straight up. If we looked at Fred was at t equals 0, he's right there. But he's always at x equal whatever that is, 5. So he's just heading straight up too. So there's Fred. Or even Francis, anyone we had here, everyone that starts with an F would just be going straight up on this system right here. They'd just be going straight up. We could even call these, there are world lines. It's how they're evolving in time right here, their position. But now, what about Mary? What if I wanted to put Mary on this? Well, we do know when t equals 0, they're both at the origin, so we know that x is also at 0, and which is x prime equals 0. So we know at least Mary is right there at that point. But Mary doesn't stay at that point because she's moving out this way as time goes on. So as time goes on, she's moving off, and so it's going to be off something that looks like this. Right here, she's heading off like that. If we look at Mark is just heading off like that too. This might be this. So this is Mary. This is Mark. If we had Mo would be going off like that too, right here. They would all be going this way. You'll notice right here, Frank, let me put Frank's name here, Frank always stays at x equals 0. So this is the x equals 0 line right here, right? So this is the x equals 0 line. And if Fred is off at x sub naught, say he's at x sub naught, this is a constant x sub naught right here. So these are constant x values right here in the black coordinate system. In Mary's coordinate system, Mark is always at x prime equals, say, 5. This would be a constant x prime value. This would be another constant x prime. So all of these lines are constant x primes. And since this is the constant x prime equals 0, that's the t prime axis right here, right? Because this is the constant x equals 0, that's just your y-axis. So this is the t prime axis right here, t prime. Okay, and so this is one way of looking at the transformation right here. Mary's just going to appear tilted over. Now, if we wanted to know how much this thing was tilted over, that is, what is the slope of this? If we were to pick a certain point over here, say this point right here, this is some time t. Remember, they agree on time. This would be t. And now if you ask, how far does Mary get out to here in a time t? Well, we know that we can say from constant acceleration equations, this is constant acceleration because v, actually it's zero acceleration, but that's still constant. We can say x is equal to x sub naught plus v naught t plus 1/2 at squared. We want to know about Mary right here. Where is she? Well, a is 0. She's just moving at a nice constant velocity, so that's 0. And her initial position was 0. So that's 0. So the amount she moves, and v is just a constant, I don't even need a v naught. The distance she moves as time goes on is just x equals vt. So this distance from here to here is vt. So I can get the slope of that line. The slope of all these red lines, the slope, which is the rise, which is t, all over the run, which is vt, which is 1 over v. So the slope here is 1 over v. Normally in classical mechanics, you put the time along this axis and the x along that direction, and the slope is the speed. But here, we're switching it. We're putting the time along the y and the x along the x, and so the slope is 1 over v. And we can see that the faster Mary goes by, the more this will tilt down right here. Okay, so now we can say, suppose we have some object that's out here. We'll put it right there, some object. Well, Frank would say that is at some position. He would say that's his x, and that was the time right there. And I'll just put it as t. That would be the t. Now Mary would say, no, that's not the x. The x is only from me to the object. So she's right there, so she would say, that this is x prime. Remember, she always measures the prime. So she would say that's x prime. And now we can see there is a relationship between x and x prime. We can see that x prime is just x minus vt. So we can say x is equal to x prime minus vt. So that is their relationship between the two. Now, I could have drawn this from Mary's perspective. Mary, she would say, no, my coordinate system is like this. She doesn't know it bent over. She'd say mine's like this. But since Frank is moving in the other direction, Frank's would be shifted this way, right here. They'd be shifted off in that direction. And if we did that, then if we wanted to get we would get the same picture right here, except we would get x prime, what is equal to x plus v x t. Now, over here, it doesn't matter if I put a prime in there or not, because t and t prime are the same. So you can see, if Frank were to come over to here, x prime is that. Let me just make sure I get x prime is x minus vt. Yeah, if Frank were over here and Mary's was straight up and down, then Frank would be x. The x would be. I might as well just do it right here. If we did it for. Here's Mary. And then Frank is heading off this way right here. And so if we have some point out there, Mary would measure it right there, x prime. Frank would measure it right here, x. And so, actually, when I wrote this down, x prime is equal to x minus vt. That's why it was x prime equals x minus vt. And from Mary's perspective, that's vt, you'd say x is equal to x prime plus vt prime. Okay, so there's, now, what you'll notice here is that any time we go from the prime to the unprime, or the unprime to the prime, x prime, right here, I might as well, sorry, I didn't mean to even say that. This was for Frank. Frank is x is equal to x prime. X is equal to x prime plus vt prime. And this is x prime equals x minus vt. Okay, there it is. Okay, so anytime you go from the prime to the unprime, or the unprime to the prime, all you have to do is change the sign of the v. So you notice when I went from here to here, I turned all my primes to unprimes and unprimes to primes. V doesn't have a prime right here, it's always the same. But you just change the sign of the v. Okay, and so with that, and we also have y prime equals y, or y equals y prime, or z prime equals z, or z equals z prime. And we also have t prime equals t, t equals t prime. These right here are what are called my Galilean transformations, right here. They're for this system where Mary's moving along the x direction at a nice constant speed, and their origins overlap at t equals 0. Now we can get their velocities also. How do they transform? Because we know the velocity is just the derivative right here. So we could say, remember, we're using ux prime. Ux prime is just defined as the derivative. Prime just means Mary's frame. Dx prime dt prime. That's what we mean by that. Now, I can take away the prime on the t because t and t prime are the same. So really, all I have to do is just take the derivative of this line up here. The derivative of that is ux prime. The derivative of this with respect to time is ux. The derivative of that with respect to time, remember v is a constant, so it's just minus v. So there's how their velocities compare when they measure something. And you remember when we go over to this side, we just change the primes with the unprimed. So this would be unprimed, ux. And this would be a prime now. And we just change the sign of the v, plus v. Okay. Well, if we take the derivative of this one right here, that just gives me uy prime equals uy. And uy equals uy prime. Same with z, uz prime equals uz. uz equals uz prime. Now we can get the acceleration because we can just take the next derivative with respect to time. If we take the derivative of this with respect to time, that's just ax prime. Derivative of that is ax. That's a constant, so the derivative is 0. Ay prime equals ay. Az prime equals az. And it's going to be the same over here on this side, just switching it. Ax equals ax prime. Ay equals ay prime. Az equals az prime. Okay, so it looks like they agree on the acceleration, all components. Well, they agree on the acceleration, they agree on the mass, and they agree on the force. So that means if in Frank's frame, he says F equals ma, if you convert that over to Mary's frame, F equals F prime, so this is going to give you F prime equals M prime A prime, which means she'll also say Newton's second law holds right here. So if they're going to, and it's not only Newton's second law, but it's his first law and his third law right here that are all going to hold. And if all of Newton's laws hold for Frank's coordinate system and Mary's coordinate system, and that means they can't tell who's moving, because the only way they could tell is if they measured something different. They all agree on Newton's laws right here. Well, that means it's impossible to detect absolute motion because of that right here. Impossible to detect absolute motion. Or it's impossible to detect if something is absolutely at rest right here. So if you have, say, a rocket ship going by another one at a constant speed out in space, there isn't any experiment they can determine to see whether this is moving and he's going, or he's at rest and he's moving, or they're both moving. It's impossible to tell right here. You don't feel movement. Your body doesn't feel movement. And that's the reason why Galileo could start tackling some of this arguments against the Earth going around the sun. We don't feel it right here. And you probably even notice it if you ever played tennis. And here's the tennis court from up above. And let's say this way is east. That's the way the Earth spins, say 1,000 miles an hour near us. And if you'd say, well, that means if the Earth spins this way 1,000 miles an hour, this might be the good side to serve from, because that way when you hit the ball, you've got the added motion of not only what you hit the ball at, but the motion of the Earth going this way. And then those people that are hitting it back, they have to fight that. And so this looks like it'd be a big advantage, but you don't get an advantage because the motion of the Earth doesn't matter. The rotation might a little bit, but not just the linear motion doesn't matter. Okay, that's so this is so that means when you took classical mechanics, there was an infinite number of ways of doing every problem in the book. You could have done it from Frank's perspective, every problem. You could have done it from Mary's perspective. You could have done it from Stan Speedy's coordinate system. There was an infinite number of coordinate systems that you could have worked every single problem at. So it should be pretty easy if there's an infinite number of ways to work every problem in classical mechanics. Okay. Now, what about momentum? Is momentum conserved in all frames right here? Well, let's just say we have some object that's moving this way, say m sub a. With momentum, we always looked at collisions. And let's say we have some other object, let's say it's just going this way, mb, but maybe slower so they'll run into each other. We'll just make this in one dimension right here in the x direction. And this is going at some UA and he's going at some UB. And then they collide, and after they collide, we'll put a little vector over here. And after they collide, this is going at some UA prime, and this is going at some UB prime. And if we wrote out the momentum equations, you would have said MA, UA, sorry, I can't use primes. that's for Mary. I'm just going to have to write after. This is after. So you got MAUA plus MBUB. That's the momentum. This is all from Frank's perspective. Then afterwards, you got MAUA afterwards. Let me just write out after. I'll put the second A meaning after plus MBUB after. Okay, now suppose we were to take all of those U's and just apply this transformation to it. Replace them all with primes plus V's. So this would be MAUA prime plus V plus MB B prime plus V equals MAUA prime plus V. This is after, I'll put a little A for after, plus MB UB plus V after. Okay, and that was all we did was use this transformation to convert it over into Mary's frame. Now you notice we have an MAV, we have an MAV. They cancel. So that term, and we got an MBV and we got an MBV. They're going to cancel because V is the same. And so what are we left with? We're left with MAUA prime plus MBUB prime equals MAUA prime plus MBUB prime. It's the same thing up here. And so if Frank says momentum is conserved, Mary is going to also say momentum is conserved. We could have also done it for kinetic energy. If this was an elastic collision in one dimension, doesn't matter if it isn't, but if it's an elastic collision in one dimension, Frank would say you got 1/2 MAUA squared plus 1/2 MBUB squared. And then afterwards, they would have said 1/2 MAUA squared after. Okay, I put a little another A there, meaning after, plus 1/2 MBUB squared after. Okay, I didn't need to put the primes on the M's when we switched it over, because remember, they're both the same, right? They would still cancel out. Okay, so now if we switched everything here to the prime, that means every place I see a UA, I'm going to replace it with the UA plus V, UA prime plus V, and this I'll just replace with UB prime plus V. So this becomes 1/2 MA, 1/2 MA UA, I'm going to replace it with UA prime plus V. UA prime plus V squared plus, and then we do it for the second one, 1/2 MB UB, which is UB prime plus V squared, and that equals 1/2 MA UA prime plus V afterwards, UA prime plus V, I'll put a little A for after, squared, plus 1/2 MB UB prime plus V squared after. Okay, that's what I get when I just transform this from Frank to Mary's frame. Now I want to know if is energy still conserved here. Well, if we look at the third term here, when you squared this thing out, the last term is a 1/2 MAV squared. And when I do the same thing over here, I'm going to get 1/2 MAV squared after, but the V is the same, the MA is the same. So that term, this third term, is going to cancel with the third term there. Likewise, the third term here is going to cancel with the third term there. So all I have is the first term and the middle term on all of these. So if I just, let's look at the middle term right here. If we just look at the middle term right here, the middle term right here will be 2 times the first times the second. But the 2 will cancel out the half. So the middle term would be MA UA prime V. We're just going to look at all the middle terms right here. And this one would be plus MB UB prime V. This one over here, the middle term, just the middle term, would be MA UA prime V after plus MB UB prime V, and this is after also, after. Okay, now we still have the first terms, but I'm just comparing these middle terms. Well, they all have a V in them right here, and so I could factor them out of these two, and I could factor them all out of there, and what would be left? I'd end up with an MA UA prime, MBU plus MBUB prime, and over here you have an MA VA prime afterwards, MB VB prime afterwards. But we already showed that those are equal to each other. If they're equal to each other, then this term is going to cancel. The middle terms are going to cancel out. They're equal, I'll just cancel them both. So the only thing left is the first term. And what's the first term here? 1/2 MA UA prime squared. So all we have left is 1/2 MA UA prime squared, and the first term of each one, plus 1/2 MB UB prime squared equals 1/2 MA UA prime squared after, plus 1/2 MB UB prime squared after. Well, you notice it's the same equation. It's just that all we did was change the primes and the unprimes. So if the kinetic energy is conserved in Frank's frame, it's conserved in Mary's frame. If momentum is conserved in one, it's conserved in the other. So everything seems to work out so nicely with this, that there's an infinite number of coordinate systems. It's impossible to detect absolute motion. Energy is conserved. If it's conserved in Frank's, it's conserved in Mary's, right here. These transformations are just a point on, in Frank's it would be like this, and in Mary's it would be, they share the same x. So this point is either x prime t prime in Mary's, or it's xt in Frank. So that's what the transformation, it's just a point on two different coordinate systems. Well, one last thing here is, suppose, in classical mechanics, they have a lot of projectile motion problems, and maybe from two different perspectives. So suppose we have, let's go back to an xy coordinate. So this is an xy coordinate, not the xt. And suppose this is Frank's coordinate system, and suppose someone throws some rock, let's just say off at some angle theta, at some u. Okay, it's going to go flying through the air. Okay, and let's just say at a specific time, right here at time t, right there, say you wanted to calculate where the object is, right? What is its x position? What is its y? What is its speed also, right there? So let's just say you're given, say, where you threw it from. Let's just call that x sub naught. That's out to here. You're given this x sub naught, and you're also given u, and you're given the theta, and you're given the time it was out here. Okay, you're given that. And let's say you want to calculate, you want to find where you are after this time t. So you want to get the x, the y, we could even say the ux, the uy, the u, and the theta. Well, I can't use that's theta, so maybe it's phi. Okay, you'd have problems like this in classical mechanics right here. And so using normally what you do is you'd list all your parameters. You'd say, x sub naught is equal to, right there where you started was x sub naught. Y naught was equal to 0 on that spot. At some later position out there, x is x was what you want. Y is equal to y. The x component of velocity, that is u naught x, looks like it's a negative u naught cosine theta minus u naught cosine theta. And the y component is positive. U naught y is equal to u naught sine theta. And the final ux is remember, the speed along this way is constant because there's no acceleration there, so that's still minus u naught cosine theta. And uy, we'll just call it uy. Ax is 0. And ay we know is minus g. G is always given right here. Okay, so if I wanted to calculate this stuff at some later point, we would just plug into our kinematic equations. We could say x equals x sub naught, which is x sub naught, plus u naught x, which is minus, so that's a minus u naught cosine theta t plus 1/2 at squared. A is 0. So there is what Frank would measure the x at some later time. The y would be y naught, which is 0, plus v naught y, which is u naught sine theta t plus 1/2 at squared. So that's minus 1/2 gt squared. So there would be the x and the y position right there. If we wanted to calculate the speed in the x and the speed in the y, we could either use the kinematic for that, or we could just take the derivative of this with respect to time. If you take the derivative of this with respect to time, actually, derivative of x is ux. That's a constant right there. The derivative of this is a constant, so it's just minus u naught cosine theta. So this is just minus u naught cosine theta, which we already knew from right here. The speed is always the same. Uy, we could just take the derivative of that equation. The derivative of this is uy equals this u naught sine theta. Derivative of that, t just goes to 1. That's just minus, bring down the 2, so that's minus gt. Okay, now if I wanted to get the magnitude of u, it would just be the square root of ux squared plus uy squared. So I could plug those in right there. And if I wanted to get the angle right there, I could say the tangent of phi equals the y over the x. So it would be for uy over ux, so it would just be uy over ux. And so I could just divide this by that and plug it in. Okay, but that's from Frank's perspective. Now, if I wanted to get it from Mary's perspective, remember Mary's origin, she's going to be right there at t equals 0 when we threw it. But by the time this gets up to here, she has moved forward. She's going to be out here someplace. What is all of these from Mary's perspective right here? Well, I don't have to go ahead and solve all this stuff out because we have these transformations. All I have to do is apply the transformation. So if I wanted to know what x prime is, I could just plug it into this. It's everything that Frank sees for x. All I have to do is add a minus vt. So from this, all I have to do, x prime is just the same thing, x sub naught minus u naught cosine theta t, and all I have to do is subtract a minus vt. So now we know we're also given that Mary is going at some velocity v right here. Okay, now what about the y? What would Mary say the y is? Well, y is the same thing. So we would say y prime is also the same as y, which is the same thing, which is just u naught sine theta t minus 1/2 gt squared. Ux. Well, if we just come to, we just want to find ux prime, it's just ux. All we do is subtract a v on it. So this thing right here, ux prime, would be minus u naught cos theta minus v. This would be a very large negative velocity. Well, I'd expect that because it's going this way and she's going that way. And so the relative speed would be larger, negative. Uy prime is the same thing. So we don't have to do anything to that. So uy prime is equal to just uy, which is u naught sine theta minus gt. If we wanted to get u prime, it would be the square root of ux prime squared plus uy prime squared. And if we wanted to get the angle that she would see, phi prime, the tangent of phi prime would just be uy prime over ux prime. I just plug those in. So it's very easy to move to another coordinate. Instead of rethinking it all out, do it from a simple coordinate system, and then you can move it to any other coordinate system that you want, right here. So everything looks so perfect in classical mechanics right here. So, but there are some problems coming up, and on the next lecture, we'll start to dig in and chip away at some of these, so you won't think it's all nice and perfect. Okay.